Welcome back after the coffee break. Now get ready to delve into the intersection of development, AI and Kubernetes with Igor Stranjanac and Filip Novovic from Bosch. In their session, they'll unveil how Bosch is simplifying NLP development in Kubernetes through their cutting-edge DataOps and MLOps strategies. Bosch is our platinum partner, and we would like to thank them for their support, and also we hope that we will continue to collaborate on our future events. Igor, an AI and machine learning engineer at Bosch, is a passionate advocate for translating complex data into actionable insights. His expertise spans applied mathematics, software development, and cloud infrastructure, particularly in AWS and MLOps. Filip, as a senior data engineer at Bosch, specializes in various database types, facilitating streamlined data management across multiple platforms. Gentlemen, the floor is yours. Please welcome.
So, hi everybody. Welcome to our presentation titled DataOps and MLOps in Bosch and NLP Development in Kubernetes Made Easy. My name is Igor, as you know now, and I'm a machine learning engineer. And together today with my dear friend and colleague Filip, we will give you some insights on how we tackle this topic in our project. So, starting from, let's say, if I figure out how it works, yes. So starting from the beginning, where we met on this project, which had a goal to use NLP solutions and build on top a knowledge graph platform, which can be used to tackle a bunch of different natural language processing problems. But also, it was kind of like a twofold project, because we wanted also to create a platform which can be reusable, but also easy manageable for researchers, software developers, so not only DevOps folks. So our team size is more or less 30-ish researchers and developers. They are divided into, let's say, 4 crucial teams, which each of them tackles some specific part of the project, whether if it's data processing, platform topics, ML modeling, knowledge graph injection, and so on. And we tackle really a bunch of business cases. We just literally threw you a bone here, just a couple of them. So one is related to the reduction of CO2 emissions. So Bosch in general from 2020 is a climate neutral corporation. So we want to also go a little bit more and to give more emphasis on this reduction until the 2030. So we are gonna tackle this. We are tackling this problem also in our project. We also want to make our requirements engineers' life easier. So whilst they are analyzing all of their technical, non-technical requirements, I don't know, costs, risks, and so on, just to do their analysis more efficiently and not spend too much time. Not in order of months, but in order, in fact, a couple of days. And we also want to, for example, standardize, automatize internal audit processes. So these are just a couple of them, but really there are a bunch of them. And since we said at the beginning that knowledge graphs are kind of like the focal point of our platform in this case, we want to give you just a little insight on how big it is. So it has like 5 million entities and almost like approximately 10 million relationships between them. So just for the people who don't know what knowledge graphs are, imagine a graph which imitates the human brain, and in fact you have nodes which represent entities and relationships between them. So any social media, if you can imagine, so let's say a friend of a friend can also be connected to me, can also get this recommendation. So that's, let's say, a very basic example of where you can use knowledge graphs. So yeah, that would be more or less about it. So I would leave it now to Filip to explain you why we do this.
Thank you.
Okay. So sorry.
Okay.
Yeah.
Okay. Thanks. So hi everyone. My name is Filip, and I work as a data engineer at Bosch Top 98 project with Igor. And today we aim to give you intuitive architectural picture. So we will not delve into some complex technical topics. We want you to gain some ideas that you can try on your own project. So we will show what is feasible and what components are used, so you can test on your own. So to simplify the picture, in a nutshell, in the project we have data processing team and ML team. Data processing team gather data resources from raw data and transform it through ETL processes, normalization, cleaning, etc. And then after we prepare the data, we push them forward to the ML team, which is a standardized approach. Then they create models and test them out. Once they are ready, they just push it into the model registry ready to be served. So this is the setup, and what we wanted to do is to create this platform human-centered, so that it is easy for everyone to use. Our data engineers and data scientists have mixed emotions with YAML files and all of those custom Kubernetes resources, so they just want to open their laptop and be able to use a Python environment. So from the data engineering perspective, we want to be able to just open up our IDE, have Python environment out of the box, and we want to be able to connect to our relational databases, MongoDB, different API endpoints without much setup. And we wanted to be able to scale our workload. So when testing, our workflows have different requirements when talking about resources. We have somewhere small amount of data that need to be processed, which is taking maybe one pod in Kubernetes or one CPU. And sometimes we have really complex data which needs to be scaled on a big number of nodes. So this was a requirement. And next, also from the data engineering perspective, we wanted to be able to easily deploy our solution. And to add on this, ML team had some other requirements also, and we're using the same platform. So they wanted to have a one-click experiment, so that it is easy to check their models. They want to change some things, try out different stuff, and then have one click so I can see my results of that model on some data. And as a last step, they wanted effortless deployment on their QA environment and also prod at one point into the serving component. So now let's see a little bit in depth how our data processing workflow diagram looks like. We have two different workflow types. So first, as I said, ETLs that gather resources from external sites and also from Bosch, also internally. So we have multiple raw data sources that we normalize, GDPR clean, etc. And then we push it into the intermediate storage, which is a SQL database. Postgres is used on our project. After that, as Igor mentioned, knowledge graph is in the heart of our project. So what we do is we take the relational data from inside of that relational database and package it into triples and push it into the Stardog instance that is on AWS. So this is what we needed to see how to implement in the platform so we can support these topics. And to see one concrete example of one ETL from the left side, so first workflow type that gathers the raw data, let's say that we have an S3 bucket in our AWS cloud provider, and we have some few thousands of JSON files. That is some standard scenario these days. So we have few thousands of files in the S3 bucket. First natural step would be to take those files and ready them for the pre-processing. So we have a gather external data. Then we can try to parallelize as much processes that we can if we want a fast ETL, so fast processing of the ETL. And right here, we can parallelize normalization and GDPR cleaning because they do not have result dependencies between each other. If we go one step inside of the normalization, for example, we can see that we can further parallelize this workflow because we can, for example, work on the first 1,000 JSON files in one pod and simultaneously work on other 1,000 in another pod, etc. So we have 2 layers of parallelization that we needed to address. And after that, we have naturally one gathering point where we combine the results from different tasks. We push it to the relational database, and then we are ready to create another workflow type, which is pushing to the Stardog instance. So this was the data processing need from our project, and now we will see the ML side of the story.
Yeah, so if you remember this, you don't need to remember it because it's almost the same thing here. So looking to the machine learning lifecycle that we had in mind is, again, to get some data from somewhere, and that we have one place where we can do experimentation, where we can do training, but also when we do it, we want to log it. So log parameters, log metrics, model artifacts, additional artifacts. So we have a, let's say, a single point of truth, which is our model registry, and from which we had also a connected component for the serving part of it, so we can have it available as an endpoint, for example, and embedded, let's say, in some other system. And we also gave some space if somebody trained something, created a model somewhere, that we have a storage which can also be where we can also stash that model, and also our model serving tool can connect to it, to that custom resource, and then create again an endpoint, which is, let's say, the end goal of the life cycle. And again, a very basic example of the machine learning training here: get some data from an S3 bucket, let's say again JSON files, and we have a couple of tasks which we do: get the data, transform it in a way that the algorithm can understand it, perform the training, get the results, log it somewhere, and later on analyze it to see whether or not if it's good enough to go further. So this was all about now all about it high level. So let's go now to, let's say, how we do it. So we don't want to reinvent the wheel, so we use GitHub as our code repository. But for example, for the compute resources that we want, since we are based on currently on the AWS provider, we utilize the AWS's Kubernetes managed service. But we need to be smart not to go, because, you know, in Kubernetes you can easily grow in costs. We have a tool which we wanted to emphasize also here called Carpenter, which is a cluster autoscaling tool, very smart one, and which gives us a very nice possibility to target specific nodes, specific machines, which we want to fulfill our processes, and that we don't need to care about it, whether or not it's gonna still be, you know, standing alive for like a month or so. So it's smart enough to understand when a pod's life is finished. So when the service finishes its lifetime, it ends the lifetime also of the machine if it's not used. So we utilize the Kubernetes resources that Filip was talking about. So we use the declarative language for the Kubernetes services, and we use GitOps, which is, let's say, DevOps framework applied to, let's say, application infrastructure development. We use a tool called Flux over here to manage all of our stages and also do the versioning part of our services. Of course, we use Terraform for provisioning AWS resources. And here comes now maybe the interesting part for you guys. How do we do really the DataOps and MLOps part? So what do we use? We use Argo Workflows to orchestrate the pipelines. But since we wanted to make something which is acceptable to all developers, to all researchers, we use a framework, which is a Python, let's say, SDK, targeted to create and submit Argo workflows. So our researchers, as you know, more or less people in data science work with Python in general. So this is very familiar to them, easy to learn, and with the proper blueprint, they will go really hand in hand. And regarding the ML system, we use MLflow and a Seldon controller, popular Seldon controller for creating and solving the model serving component of our system. And at the end, all of these tools are very secured, since of course we are Bosch and we need to have this on a very high level. So with single sign-on, machine-to-machine communication, and all sorts of different kind of security steps. So let's now go a little bit deep into how the development flow goes.
So we, as we said, try to make this easy for developers. Now let's see what is expected of you as a developer. It doesn't matter if you're a data scientist or data engineer, the flow is the same. So first, you would need to create your GitHub repo, which we do through Terraform. So we use infrastructure as code for every resource that we can on the platform to make it easy to shift it from dev to QA to production, etc. So after you create your repo, you can use some of the blueprint templates that we created for multiple repeated scenarios. And then on that repo that has a template, you would open a branch that represents your feature, so what you want to implement. Now, we use some nice tool. I don't know if you used it, but I would propose to try it out. GitHub gives a possibility to have IDE integrated into the browser. So it is called GitHub Code Spaces. And it gives you a possibility to customize your environment online. So you don't need a client machine with all those proxies set up and access for data sources. So now that you have a branch, you would open your GitHub code spaces on that branch. You would then customize your environment. So it is a Visual Studio Code environment that is defaultly used in the code spaces. You would edit your requirements TXT to match your libraries that you need. For example, data engineers would use PsychoPG, for example, for data processing needs or accessing Postgres. On the other hand, ML scientists would use PyTorch. So here is the place where you customize it, you edit your source code, and after you are ready to test out in the development phase your workflow, you call one-line script that we created for Bash that is running on that code spaces instance that dockerizes your whole environment. So it creates a Python environment from your requirements TXT, and it pushes your source code that you've written, so where is your business logic, inside of that Docker image, and it calls it ephemeral Docker image because it lasts for 1 day. There is no need in dev cycle to use to store for long periods of times, like months or years. So every Docker image is deleted after a day. So we don't need to use memory that that can be free. So after that image is created and we have our source code and resources in it, we can say to our Hera tool that Igor mentioned, okay, run my workflow that I've written in pure Python with the usage of Hera library with this Docker image. And then it just says, okay, it runs it on Kubernetes cluster, and you can get your resources very quickly. So it is a one-line call of that. And at one point, when you are ready to merge this and switch it to deployment, you follow the next steps.
So in the next step, you would obviously, as a good developer, you would like to merge your pull request, and all sorts of stuff happen when you do this merge. What we wanted to emphasize over here is that we finally get a fully blown version of an image which has your business logic in it, and that's the first step. And later on, based on that image, a YAML file is produced, an Argo YAML file, which is a template, which can, based on it, Argo in fact schedules your stuff later on. So once the image is done, the YAML template is created. You can also have a bunch of other stuff. It's very flexible with GitHub Actions and workflows. It gets merged to the main branch, and now comes maybe a very interesting part, I would say. So bear with me now. So this is, like I told you, the GitOps principle that we use. So again, it's a DevOps framework for easily infrastructure automation and application automation. So what we do, imagine, let's say, on a very basic example, that you have a Git repository where you have like 3 folders. Each folder represents your stage. One is development, one is QA, one is prod. In each of those folders, you have your Kubernetes resources defined as YAML manifests, usually in this case, that we do. And it, in fact, represents the state of your stage in, let's say, a declarative language. And we have a Git operator, which you see in the middle, which listens to any change which happens in those specific directories, which are, again, the state of your system. Once it checks something, so a commit comes in, it checks the state has changed, it listens to it, pulls it back. And then there's the next tool which occurs, which starts, called customize control, which analyzes the new state and does a process called reconciliation, so to, in fact, create the appropriate state based on the information that it got. So in our specific case, once some change happens, whether we are talking about data processing, machine learning training, or even machine learning serving, in the first two occurrences we use Argo templates. In the later one we use also Seldon template, which is, all of them are in fact a single YAML file which is being used. It does the reconciliation process and in fact schedules pods in how many you need. So whether or not we are doing some kind of a parallelization or just at the end doing some model serving task and creating a microservice at the end, let's say like that, which is fully secured and so on. So it creates and schedules those pods. They do the business logic that you want, they analyze, do the processing which you need, and as a result they go, if we are talking about data processing, to some storage. If we are talking about machine learning training, to our model registry. And if we're talking about Seldon, it has a different output. It's in fact, the output is, like I told you before, a full-blown endpoint, which is, again, with a lot of stuff done in the background related to ingresses and so on, secured and ready to be embedded in any other system as a REST API. So in fact, this was the main kind of point that we wanted to kind of figure out, and where we found that the data processing and machine learning concepts kind of overlap. So now we would, after this deployment flow, after telling you this, we would like to give you a couple of words at the end.
Thanks. So next steps and where we are now. First, every workflow has its own resource requirements, and what we want to do is cost optimize it. So we want to introduce metadata that is not created ad hoc, so that we can know for each workflow how much CPU is needed, how much memory, and possibly GPU for model creation. So next, we already did the second one, although we are integrating it into our workflows. So Argo is a complex platform that keeps evolving on daily basis. And they have a component named Argo Events, which gives us a possibility to trigger our workflows. For example, we'll stick to that example of S3 bucket and JSON file. It is possible to create a scenario where you drag and drop your JSON file into the S3 bucket, and automatically Argo Events gets that event and runs your workflow. So we are pushing this technology into our workflows in the future. Next, this is also my proposal and what we did on this project. We were in constant cooperation with Hera developers and Seldon support. We wanted to give them a live feedback of their platform, and because we thought maybe they can have some input out of it, and they did. So why is it a proposal? It would be nice that if you are working on some new features and the edges of the tools that exist, feel free and called to say that to the original team that is behind it. Maybe they will get some nice data out of it. Next, I would say that naturally with the maturity of our platform, we plan on adding data versioning and feature store to make it easy to follow both processes of data engineering and ML engineering. And also, right now we use Datadog for computational monitoring. But at this point, it is not sophisticated enough. It is good to follow what happens under Kubernetes shadows. But we want to add sophisticated monitoring where we can see how our model behaves through time, so in real time. And also that is same goes for ETL pipelines. We want to see how much data was processed, how long it took, what are the costs. So working on monitoring will be definitely a huge topic in the future.
Yeah, and we wanted also to highlight a couple of recommendations which we want to give you. So when you start to build your system, you have your business use case, be free to experiment, be free to do POCs with your tools that you're using, that you want to use in your design decision, because it is really helpful, and until you really try it out, you won't really know what it can do. But also when building your system, since scaling is a very important topic now, don't forget about it. Create a system which can handle thousands and thousands, in this case, pods, which can be scaled on different kind of nodes, using different kind of even GPU nodes, like Filip said. But don't get into the trap that you get something over complex and over complicated, because think about for whom you're building it. You're building it for researchers, in our case, for data engineers who just want an easier way to deploy their services. So follow the KISS principle and keep it small and simple. And as a last point that we wanted to highlight is separate your tasks. So separate your, in this case, we say DAGs, but separate the task that you want to do from your business logic and create reusable code more or less whenever you do, since that helps us a lot because of our multiple business use cases that we had. We could reuse a lot of stuff again. So with that said, I think this is the end of our presentation. Thank you for listening, and we are open now for your questions.
Yep.
Great presentation, thank you. Just one question regarding the graph database that you chose. Have you considered using GraphQL instead of StarDog?
Yes, we considered even using Neptune in AWS, but looking to even the costs, the complexity which you need to build around it, StarDog was, even from the point of managing StarDog itself, it was a really no-brainer. So it gave us, it's kind of like a commercial marketing point, but for StarDog, but really, it really helps. It's really easy to manage it.
But StarDog is only enterprise, right?
Yes, yes.
Thank you.
Okay, we have a question there.
Hello. Have you considered using MLflow instead of building your own containers and YAML files, etc.? Because these are already provided by them.
Yes, Kubeflow, MLflow, all the other flows. But again, comes to complexity and comes to the KISS principle. So in one hand, you had a lot of researchers which didn't have a clue about MLOps, also data engineers which didn't have that much knowledge about the ops part of it. So where we stepped in and tried to find a way how to make it easy, manageable, so to not get too much emphasis if something breaks, that all the stuff breaks. So MLflow seemed to us at the beginning in the design decision quite complicated to manage. As well, a very similar answer to the startup one.
Okay, we have a time for one more question. Okay, yes, please.
Hi. So you're using Argo for workflows and events, and why not use it for GitOps also?
Well, we already set the infrastructure to use Flux as a controller, so we had that thing going, and there was no need to change it. There is a possibility to maybe apply it in the future, but we do not change all the technologies when we introduce anything, because that gives us a possibility to be flexible in trying new things and not burdening ourselves with moving all of the tech stack to other stack. Thank you.
Okay, that's all for today. Igor, Filip, thank you very much for being with us. I would like to express our gratitude to you. Filip, this is for you.
Thank you.
And Igor,
Thank you.